going to discuss on a silicon transfer in blast furnaces. Ever wonder why some iron making operation just seem to run smoother and cheaper than others? Here is the thing. It usually comes down to how well they are handling silicon. You are looking at a screen filled with the glow of molten metal pouring from a furnace. It's intense, orange and look like liquid sun. That stream is the lifeblood of the plant, but if it's packed with too much silicon, we have got a problem. Today, we are not just looking at chemistry, we are mapping a blueprint. By the end of this session, we will have defined the three stage gas liquid transfer route, identified the thermodynamics lever used to suppress silicon gas, and established a practical strategy for hitting those ultra low silicon target. This is about identifying the hidden gas route and the chemical tug of war that determine our pig iron is top tier or costly headache. But before we talk about how it moves, we need to talk about why we care so much about the final number. The critical role of low silicon pig iron. So what behind a low silicon number? On the screen you see heavy grey pig iron ingots stacked up. They look solid, but their chemistry dictates the entire budget. If we can keep that silicon low, ideally between zero point 0.3 and 0.4%, our furnaces becomes a beast of efficiency. Why? Because lower silicon means we use less fuel and get more iron out every single hour. Plus, in the steel shop, they don't have to spend as much time or money cleaning it up. So, what? The lowering silicon is not just a technical goal, it's a massive save money button for the whole plant. To hit those low numbers, we have to track the secret agent of the furnaces, SIU gas. Coming to the our next slide, which elaborate on the silicon transfer route. SIO gas. Here is the aha moment. Silicon doesn't just fall into the iron, it hitches a ride on a gas. You see a close up of glowing porous coke, it's the black gold of the furnace. Inside those high heat zone, the silicon in the coke has turned into SiO gas. Think of it like a silicon rich steam rising up through the furnace. As the iron droplets fall down, they act like little sponges, soaking up that gas as they pass through. If we don't control that gas generation at the bottom, the iron is preloaded with silicon before it even reaches the hearth. So if the gas is the vehicle, what are the speed limit we can enforce? So coming to discuss on next slide about our thermodynamic levers. If we want to stop that silicon sneaking, we have to pull three main levers. Look at these icons: a thermometer, a pressure gauge, and a flask. First, temperature. High heat is like fuel for silicon gas. Keep it cooler and the reaction slows down. Second is the pressure. If we crank up the pressure inside the furnace, it literally squashes the gas production, keeping the silicon trapped in the ash. Finally, the SiO2 activity. By injecting things like MgO, we change the chemistry basicity, making it harder for the silicon to break free. This is our primary defense, changing the environment so the silicon simply stay put. But thermodynamic is only half the battle. We also have to look at the clock and the whole thing, who is who of silicon sources. Coming to the kinetic factors and the control. So, where is the silicon actually coming from? Check out this pie chart. That massive 70% orange slice. That's the coke and the coal ash. Most people think the slag is the main culprit, but it's actually the fuel itself. Only 20% comes from the slag metal interface. So, what is the result? This means if you have dirty coke with high ash, you are fighting an uphill battle from the start. You cannot just fix it with slag chemistry. You have to look at your raw material quality first. Now, let's zoom into the most chaotic part of the furnace, the dripping zone. Coming to our next slide, which elaborate on the dripping zone dynamics. So imagine a giant high-speed obstacle course. That's the dripping zone. This table shows us how the physics of the furnace affect silicon. If iron takes longer to fall, what we call residence time, it has more time to breathe in that SiO gas, and silicon goes up. If you use bigger coke, the iron drip through faster and silicon goes down. Even the thickness or the viscosity of the iron matters. Basically, anything that slow down the iron's journey to the bottom is going to increase your silicon content. But here is the weird part. Sometimes the silicon actually goes down once it hit the bottom. So, next slide, which completes our study on desiliconization in the hearth. So, here is a twist. The silicon content actually peaks before the iron reaches the pool at the bottom. Look at these icons for the droplets and levers. Once the iron hits the slag layer in the hearth, a cleanup reaction starts. Elements like FeO and MnO in the slag act like magnets, pulling the silicon out of the metal and back into the slag phase. We call this desiliconization. If we keep the hearth at the right temperature and high basicity, we can actually scrub some of that silicon away at the very last second. So, how do we put all these moving parts into a real world game plan? So, our next slide exactly hit on the operational strategies. If you are the operator sitting in the chair in control room, what do you actually do? It's a three pronged attack. First, you clean up the input, reduce the silicon in your raw material. Second, you pressurize the system by raising top pressure to keep that gas under control. And third, you fine tune your slag using MgO to make sure it's ready to soak up any silicon that makes it through. Doing these three things in synchronization is the difference between a furnace that struggles and one that sets production record. But we are moving beyond just manual knob turning. So, coming to the path forward, finally, where are we going? You see a frustrating control room with massive blue data screens. We are moving away from the guessing and towards AI and big data. We are building intelligent models that can predict the silicon level in real time, allowing us to adjust the blast parameter before the silicon even has a chance to rise. The goal is precise control, using every bit of data to keep that furnace in the sweet spot of low silicon, high efficiency production. Any things which are abnormal also being taken care by such a stable operation. So applying these levers to our current operation could able to meet our objective